So, moving forward, I would like to introduce what is called as a Miller's index. So, I would potentially introduce these Miller's indices and concepts of reciprocal lattice, and then we will switch back to the ideas on how you obtain diffraction patterns in TEM. So, if I think about Miller's index, if I see how my crystal structures are, and if I think of a crystalline lattice which is in 3 dimensions, I have to first choose an origin, and any point within this which is given by a positional vector, say r bar, which is, let us say, in this case the example shown here is given as u v w. So, essentially if I think of the unit vectors being a bar, b bar and c bar here, for any point which is randomly positioned at a distance, say x, y and z in 3-dimensional axis, when I want to write the position vector for this, I can always write it in terms of some r bar is a dot u plus b dot v plus c dot w, where this point I can define in terms of some unit vectors which are along my unit cell vectors. For any given point, if I want the Miller's index for a direction, so let us say if this is in terms of some scalar h a bar plus k b bar plus l c bar as the vector that is connected to a point HKL, these unit values or these scalar values when multiplied with the unit vectors of my unit cell are what are called as Miller's indices for direction. And likewise, I can also have Miller's indices for the plane as well. So, let us say I have a plane which is intersecting a hypothetical origin within a unit cell. If I have a plane which is intersecting, I can get the Miller's index for a plane by first projecting a plane normal. So, let us say if I have this plane corresponding to some indices h, k, l, if I draw a plane normal, I can represent this plane normal with a direction vector h, k, l as well, and in terms of my unit lattice vectors, I can get some values of intercepts which are intersecting on my x, y and z axes, which I have defined to get the Miller's indices. And what I get here is, if I want to get a direction vector, if I want to get Miller's index for a direction, I can simply write a position vector in terms of the unit vectors. But if I want to get Miller's index for a plane, I have to first take a plane normal and then identify direction vectors of a plane normal. So, with this I end up getting Miller's index for a plane as well. Let me show this with a very simple example. So, if I look at this case here again, so let us say in a unit cell which is shown like this in the cube that I have here. If I think of my origin, so typically the convention is the farthest leftmost point, which is inwards here. If I define this as the origin, this is the common convention I have here that we use to give Miller's indices. I use the right hand coordinate system, and if I say in this direction I have my x direction, and if here is my y direction, if I take a right hand coordinate system and I take a cross product, my z direction is here. My unit vectors, because it is a cubic system, are, let us say, a bar and a bar, and they are all corresponding to a value 1. This particular point, I can now index this as 0, comma. So, this particular direction is now actually 0, 1, 0, and this direction is 1, 0, 0, and this direction is 0, 0, 1. And now, so I simply got the direction vectors by connecting one of the unit vectors with the origin, and I draw the position vector for this. I get the Miller's index for a direction. But if I want a plane, let us say this plane which is here, I can do it in two ways. The conventional geometric way of giving a Miller's index for such a plane is, I take the points where this plane intersects my three-dimensional axis that I have drawn, and I say this plane intersects my y-axis at 1, whereas it does not intersect my x or z-axis. So, I have to take the value of intercepts as intersecting x-axis at infinity, intersecting y-axis at 1, and intersecting z-axis at infinity again, and then you do the step of taking the reciprocal of these intersection points, and then you say that my Miller's index for this direction is 0, 1, 0. So, that is how I get the Miller's index for a plane, but a simpler and a more logical way is, for this particular plane, I simply project the plane normal, and the plane normal in this case, which passes through the origin, is the direction vector corresponding to 0, 1, 0. So, I can say if I have a plane with indices h, k, l, the usual convention to give Miller's index for a plane is with these parentheses, or if I have a family of planes, I give it with this kind of a bracket, a flower bracket. The Miller's index for a plane corresponding to HKL is usually the direction vector of a plane normal with the indices HKL. That means for any random plane. So, let me take this asymmetric system now. So, let me take a body diagonal plane which looks like this. Let me connect this point to, so if I have a body diagonal plane like this, if I want to identify the Miller's index for this particular plane, I simply take a plane normal of this and I go through the origin, and I know that this intersects my x, y and z axis at 1, 1 and 1. So, my direction vector here is 1, 1, 1. And therefore, this becomes my plane normal, and my Miller's index for the plane here for this direction becomes 1, 1, 1. I can do it in two ways. I can either take the intercepts with the respective x, y and z axes here and then find out, or I can simply get these plane normals and connect them with the origin and then get the Miller's indices. Now, what is the whole objective of showing you the concept of these Miller's indices and establishing that when I have Miller's index for a plane, its corresponding plane normal also has the same Miller's index value. If I want to introduce a concept called as reciprocal lattice, what this helps me is any direction vector corresponding to the plane normal can become a reciprocal lattice vector where I can represent a set of planes with help of a unitary plane normal. This idea becomes very useful when I am trying to index my diffraction patterns. So, with this, let me introduce how a reciprocal lattice is constructed. We will take the simplest example of a two-dimensional reciprocal lattice. We will look at a projected reciprocal lattice of a three-dimensional system and then try to relate this with an electron diffraction pattern. So, if I have a simple oblique lattice as I see in this figure A here, by definition a reciprocal lattice can be thought of as the lattice which is constructed by 1. If I have a real lattice and I have the unit vectors of a real lattice, if I can think of an imaginary lattice where, so let me write the reciprocal lattice with another color. Let us say by definition, if my real lattice has unit vectors and if all the planes of my real lattice have their corresponding plane normals, we define reciprocal lattice as the lattice constructed along the plane normals of a real lattice. So, let us say I have a set of planes 2 and 3 here. If I draw the plane normals of these, the direction of plane normals are like here now, and if I take my reciprocal lattice vectors along the plane normals, I end up constructing a lattice along these directions. So, in principle, a real lattice which appears like this can be transposed or can be related to a reciprocal lattice by simply doing a few simple operations. For simplicity, we have now started looking at plane lattices and we are trying to build a concept of a reciprocal lattice as an imaginary lattice constructed along the plane normals. So, if I take a unit cell vector as HKL and let us say this corresponds to a family of planes HKL. If I think of an imaginary lattice which has coordinates as H star, K star and L star, by definition these reciprocal lattice with indices H star, K star, L star would be along the plane normals of a real lattice HKL. This is just a mathematical definition. And once you have this, for simplicity, we have brought some relationship where we think that the volume of the unit cell comes into picture, and we defined that the dimensions of reciprocal lattice vectors are inversely proportional to the real lattice vectors, and you can relate these through the volume of a unit cell. I will not go there yet, but the whole objective is to essentially build a concept that when I have a real lattice and I take the plane normals of the real lattice and I construct an imaginary lattice along these plane normals, I end up getting a reciprocal lattice. Let me simplify this by showing you an example of a reciprocal planar lattice constructed from some primitive planar lattices. For example, if I have the oblique lattice here and if I take the plane normals of these oblique lattice. So, I have a simple plane normal like this and the other plane normal like this. Now, if I use this as a unit vector for my reciprocal lattice, this corresponds to this vector A star as shown here. So, the planes that are separated by unit vector A, if I take the perpendicular of those planes and I represent it as A star, and the planes which are separated by a spacing B, and I draw the perpendicular which is here, and I move this and I construct a reciprocal lattice with this, my oblique lattice which is appearing like this appears to be transposed to an oblique lattice which appears like this. If I use the same idea for a rectangular lattice here, my A star is along the perpendicular of these planes, which is, so the planes which are separated by A, my A star is like this now, and the planes which are separated by B, my B star is here. It appears as though my real lattice, the real planar lattice, has been transposed by a 90-degree counterclockwise rotation. So, this is something which you will see in a projection and a Fourier transform that you take in a high resolution TEM image as well. And also when I look at the real space versus reciprocal space relation within a TEM, I usually end up seeing this sort of a 90-degree rotation. That is because the diffraction pattern I obtain in an electron microscope is actually a projection of the reciprocal lattice, and this idea of reciprocal lattice is obtained by constructing a lattice along the plane normals. Now, because I have this concept of reciprocal lattice as constructed along the plane normals, it appears like you have a sort of a rotation. The same applies true for this hexagonal lattice. In real space, if this is my hexagonal lattice, it appears like if I now take this and rotate it by 90 degrees, I obtain getting this. And the same holds true for a C-centered rectangular lattice, and you do not see this rotation pronounced in a square lattice, but in a more asymmetric system it becomes more evident. So, with these ideas, if I now take a projection of a very asymmetric 3-dimensional lattice, so let us say I have a monoclinic system, I have a unit cell projection like this, and the projection of this, when I visualize along the reciprocal lattice, it appears like this. So, and then if I now build in 3 dimensions and I look at the reciprocal lattice in 3 dimensions, let me go back to this slide here again. I can think of a reciprocal lattice of a cube constructed along my perpendiculars or the plane normals, and cube being a very highly symmetric structure, the reciprocal lattice appears exactly like a cube real lattice only. But for our convenience and to understand and relate this with the so called Ewald sphere and the inverse relation which is introduced to the real versus reciprocal lattice, I can think of reciprocal lattice as a concept such that my dimension of a unit cell vector, let us say this is B here, my B star would be inversely proportional to B, and I can dimensionally relate them through a simple volume of a unit cell and compute depending on a few parameters. So, if I am using X-ray diffraction, the value of my X-ray wavelength comes into here, and I can relate my unit cell vector to a reciprocal lattice vector through the wavelength that I use here. And likewise in electron diffraction as well, there is something called as a camera constant, and I can always start relating these real space vectors to reciprocal space vectors. Now, what people have done is to understand these projections and the relation with the reciprocal lattice to real lattice through plane normals. They have devised the concept of something called as a stereographic projection. I would like to show you this stereographic projection over the next couple of slides. It is again a mathematical concept where I am trying to relate the poles or projections of plane normals through a special concept where I can imagine a sphere surrounding a unit cell, and I take the plane normals, and the projections of whatever I get from these plane normals or the poles are called as pole figures, and then we start seeing how the reciprocal lattice can be projected, and this becomes very handy to understand electron diffraction patterns.